Hello, in this video we're going to be talking about the contextual applications of derivatives, specifically with velocity and acceleration, that we might proceed at high velocity. If we're given a position function, so something is moving around, and usually it's called s of t, y, I don't know, that's where it starts. If we take the derivative of that, that is telling us where it is with respect to time. So as time changes, where is it ending up? That is what velocity is. That as time changes, where do we end up? If we do the derivative of this, this is telling us how quickly that change is moving. So what is the change of the change? That second derivative tells us the acceleration. So velocity is like kind of how fast a car is going. And then acceleration is like pushing on that accelerator to make the car go faster, or pressing on the brake to, even though still going forward, reduce that forward velocity of a car. So in this example, we have a position function right here, and we want to figure out what is the displacement during the first 5 seconds. Well, what displacement means is how far has it moved? So in those 5 seconds, how far has it moved? Well, it would help if we knew where it started. Well, that's not too hard to find out. We can take our t of 0, and then we can plug that in. So its position at time 0 is 2. That's where it starts. And then in the first 5 seconds, after 5 seconds, where does it end up? Well, we can plug in 5 and then we get 12. So we know that over those 5 seconds, it's moved from 2 to 12. So its displacement is 10. I know it's 10 because we started at 2 and we moved to 12, so that's 10. And I know it's going to be meters because in the problem they said S is measured in meters. And I also didn't have to do anything funny with time because time is measured in seconds. In part B, I brought over the information from part A. We want to find the average velocity during the first 5 seconds. Well, that average velocity is talking about derivative. Velocity is similar to what is the slope of the position. So we're finding the average rate of change from these 2 points. So we can just plug that into our Born-Arnold slope formula, and we get our answer. I'm going to clean this up a little bit. The average velocity during the first 5 seconds is 5 meters per second. Do we always need to write those sentences? No, but it is kind of nice to be in that habit should they be looking for that. In this example, we're looking for the instantaneous velocity when t equals 4. So that is now talking about the derivative. It's not the average, it's the instantaneous. To find velocity off of a position, we need to find its derivative. So here I found the derivative of s at 4 and just plugged in those values. So the instantaneous velocity when t equals 4 is 5 seconds. Let me clean that up. There we go. The instantaneous velocity when t equals 4 is 5 meters per second. To find the acceleration of the particle, we need to take the derivative of s prime, because this is v of t. To find a of t, we need to figure out what is the derivative of v prime. Or you can also just say, hey, we need s double prime of t. So the derivative of that thing is going to be just 2. So finding it when t equals 4 is easy. The acceleration is constant. It's constantly accelerating at 2. The acceleration of the particle at time t is 2 meters per second because we've done a derivative of a derivative, so we get an extra per second. We added 1 when we did the first derivative. We're at another per second when we do the second derivative. You can also write this as meters per second squared. Either one of these is fine. In part E, we need to figure out when the particle changes direction. Now, an important thing about velocity is velocity cares about sign. If we're positive, we're heading in one direction, usually to the right. If we're negative, we're heading towards the left. The times that it wouldn't be is if it's like in the context of the problem, it's saying like, oh, it's a boat traveling north versus south. That will give you the context clues that it wouldn't necessarily be right and left. But if there's no major things, like I don't see any of that in here, I would just assume that positive is to the right and negative is to the left. So we just need to know when this velocity function changes sign, when it changes from positive to negative. A good way to check that is to see when it equals 0. Time t equals 3 halves. Now, if we had gotten any negative answers, we would have ignored that because this is only when t is greater than or equal to 0. So that would be the time that its velocity is 0. And if I think about a linear, anything less than 3 halves is going to be a negative value, and anything greater than that is going to be a positive. So that is the time that the particle changes direction. So to answer, we would say the particle changes direction at time t equals 3 halves, since the value of the velocity equation changes from positive to negative at that point. In this example, we've got a nice position function. We want to find the body's acceleration each time the velocity is 0. So velocity is going to be the derivative of our position, because that's going to talk about when the position is going to be changing every time our time changes by a little bit. That's what derivative asks about. Change in position with change in time. So this is our velocity of our particle, and we just need to figure out when this thing equals 0. So I'm going to do a little bit of solving here. So the 2 times that our velocity equals 0 is at time 3 and at time 1. Now we need to figure out what the acceleration of the particle is going to be. So that is s double prime of t. That is telling us the acceleration of our particle at any time. So that is going to be 6t minus 12 for our acceleration equation. So then we need to just put those two values into there. So a of 3. So at time t equals 3, the velocity of the particle is 0, and the acceleration is 6 meters per second squared. And at time 1, the velocity of the particle is 0, and the acceleration is negative 6 meters per second squared. Those are the two answers written out in a nice sentence format, so that it's very clear about what our answer is. In this example, on Earth, in the absence of air, a rock is thrown vertically upward from the surface with an initial velocity of 24 meters per second. And then we got position function. We want to know how high the rock is going to go. Now, the way things go when you throw them is they go up velocity that is positive, and then that velocity switches to negative. So it is going up and then it comes down. So we want to know when that velocity switches from being upward to downward. So where it changes that sign. So we got to figure out when the velocity hits 0, because that's where it will change from going up to going down. Once we know what that time is, we'll figure out what its displacement is at that time. So s prime is our velocity. So that is 24 minus 4.9 times 2 is 9.8 t. And we need to figure out when this thing equals 0. So that is 24 minus 9.8 t equals 0. That's just a little two-stepper. So I needed my calculator for a little bit of help, and I got t equals 2.449. T is approximately 2.449. So that's when it reaches the top of its curve. We need to figure out what the displacement is at that time. You don't have to do anything fancy with it since it is thrown from the surface, because we want to know how high up it goes. So that's just a matter of plugging in that 2.449 into here. And I get 4.776 meters. So we would say that the rock's highest point is 46.776 meters. I think I said the wrong number here earlier, but you get the idea. Woohoo! That is the end of our velocity and acceleration video. So again, when we're taking that position function, we find its derivative, we're seeing what is happening with its position with respect to time. That's exactly what derivatives find, is what is our change of position with change of time, dx over dt. Proceed with high velocity. Goodbye.